start with the glimpse of VS-EPR theory you have studied earlier. So,
Yes, sir.
yeah. So, VS-EPR is a theory which helps you to predict the arrangement of uh,
The molecules.
bonds and lone pairs around a central atom, and help you predict uh, the most optimal way to arrange these um, just one second,
So
arrange
it's
this valence shell
valence shell electron
electron
pair
pair
repulsion theory, right?
repulsion. Let me write it. Yeah, valence shell electron pair repulsion theory. Okay, so what this theory talks about is that we know, you take any bond, again any covalent bond between atom A and atom B. You have a single bond, and this single bond is comprised of two electrons. One comes from A and one comes from B, and they share these electrons in the internuclear region, and as a result, a bond is formed. Okay. Uh, so when there is a molecule with multiple bonds, it's a good thing that the bonds are formed because it contributes to the stabilization of the molecule. But at the same time, there's also repulsion between the electrons. First of all, it's a mystery how two electrons occupy a single orbital, because they both have the same charge, so they must be repelling each other, but still they manage to stay in the same orbital. That itself is a great mystery. I mean, if you go to quantum physics, you can definitely spend the next 50 years of your life probing that idea. Okay.
Excuse me, sir. Can I ask
Yeah.
something?
Yeah.
So, firstly, we learned that metals donate electrons and non-metals, metals donate electrons and non-metals accept electrons. And here we are studying that they share electrons. So, what
Mhm.
is true?
Because okay, so you're talking about metals donating electrons. So okay, so let's take
To
example.
attain a positive charge.
Yeah, so let's take the example of sodium chloride. So in sodium chloride, we never write a picture like Na bond Cl. We'll never write like this. Okay, the reason is this is an ionic compound. So which has ionic bonding, where sodium has a positive charge and chlorine has a negative charge, and it's pure electrostatic attraction between the positive charge sodium and the negative charge chlorine. So whatever picture that you are talking about is an ionic compound. Whatever I am talking here, the sharing of electron happens in covalent molecules.
But for
Okay, so this
covalent bonds, we
mm,
represent it with an arrow, right?
no. Why don't you ask your friends? Do we represent covalent bonds with an arrow, guys?
Only
Sir, only
coordinate bonds,
coordinate
sir.
bonds.
Only
Sorry, sir, I got
coordinate
confused.
bonds or coordinate covalent bonds are represented with an arrow. Correct? So let's take an example. Um, diamino silver. Okay, so you have silver and you have two ammonia molecules, and they are represented this way. And here it's a coordination complex, so you put square brackets, and of course maybe a positive charge over the complex. And here in this case, you talk about ligands and metals. So here metals receive the electrons. Um, so these are the basic three different kinds of compounds that one comes across: ionic compounds, covalent compounds, and coordination compounds. Okay, so in this, I am not talking about ionic compounds. I am not talking about covalent compounds. Sorry, coordinate compounds. I'm talking about covalent molecules. So how is a covalent bond formed?
So by sharing of electrons.
By sharing of electrons. So that's the picture I'm painting here. Okay, so the stability that is derived by the sharing of electrons is uh, uh, disturbed by the electron-electron repulsions, the electron pair repulsions. Okay, so that's how the VSEPR theory came into being. Scientists trying to figure out in different covalent molecules. This particularly applies for covalent molecules. So if you want me to give you some examples of covalent molecules, here are some of them. You have water, you have ammonia. I'm going to give you quite a bit of covalent molecules for you guys to explore through Avogadro. Okay. So I'm going to give you quite a few a little later. So, so electron shell, uh, electron shell, valence shell electron pair repulsion theory tries to predict what arrangement of these electron pairs should happen around a central atom so that the shape is optimized, so that energy is minimized. See, you have to understand why a bond forms in the first place. I don't know if you have ever studied the formation of hydrogen molecule. You see, hydrogen single bond. There's a sharing of two electrons between these two, and there's this very popular potential energy graph you might have studied in your lower classes. So this is the potential energy, okay, in increasing order, and this is the distance between. Have you guys studied this?
Yes, sir.
Yeah. So the two atoms. So when they are really far away, so there is this zero level. Okay, so this is zero level. Sorry, I put zero here, so not here. Okay, so I'm kind of brushing up so many old concepts that you might have studied. So you come from infinite distance, okay, and so the energy between potential energy between hydrogen and hydrogen is zero at that level, and then as they are coming closer, the energy starts dropping. The reason for the drop in the potential energy is because there are favorable forces, attractive forces happening. What are the attractive forces? You have hydrogen number 1 and hydrogen number 2, the nuclei, the two nuclei. So let's call it A and B. And there is this s orbital, and it has an electron. So let's draw the electron in a different color. So you have an electron each. So as they are coming closer to each other, you have attractive forces between the electron of A and the nucleus of B, the electron of B and nucleus of A. So these attractive forces are acting on each other, bringing the potential energy down. Okay, so so we call this as stabilization. In thermodynamics, you might have studied about stabilization. Okay, and it keeps going down until an optimal distance is reached. That's where the two hydrogen atoms have the lowest energy. So it reaches that, and then any more pushing closer A and B atoms, hydrogen atoms, will only increase the potential energy. And the increase now is very, very steep. It's a very fast increase. So it looks something like this. Not drawing so well. Okay. And the reason for such a steep rise is After the optimal distance, if you bring the A and B any closer, more than the attractive forces between the electrons and the protons, the repulsive forces will overtake. So the repulsion is between the nucleus of A and nucleus of B. That is the more prominent repulsion, and it starts rising really, really fast. Okay, which means that you can have the atoms separated by infinite amount of length, but once the equilibrium length is reached, you cannot squish them any closer than this equilibrium length. You can a little bit, but not more than that. Okay, so this equilibrium length is what you called as the bond length. Now, why am I telling this story? Now I'm telling you what is the reason for a covalent bond to form. Covalent bonds are formed because of the attractive forces between the adjacent nucleus and the electrons. Okay, so the attractive forces stabilizes the entire system, and as a result, covalent bonds are formed. But please remember that here in the case of a hydrogen molecule, there is electron repulsion. Okay, but in the case of, let's say, you take an example like methane, sorry, CH4, you don't have just one or two electrons, you have many electrons. You have a carbon at the center, and you have a hydrogen, 4 hydrogens. Here, for convenience, I'm drawing it like a cross-shaped molecule, but methane is not cross-shaped. We'll come to that a little later. Okay, so all these electrons have to be arranged in such a manner that it should result in stabilization and not an increase in the potential energy, not a higher level of energy. Okay, so in order to achieve that, once the molecule forms, the bonds, these bonds have to orient themselves around the central atom in such a way that maximum distance is maintained between the electron pairs, so that the maximum possible levels of separation is maintained. It's like in school you used to do this. No, you used to stand in the ground for your prayer assembly, and they ask you to stand a little apart from each other. You have big lines, right? So something like that. So you want to stand apart. So you don't stand too far away that you lose the attractive forces. You don't come too close so that the repulsive forces overtake. So somewhere in between. So the optimal length and the angles.
Sir
Okay. So
means
in case of
equilibrium position.
sorry,
Means
equilibrium,
equilibrium position, sir.
equilibrium position. Correct. Equilibrium position is the right word. Okay. So in a diatomic molecule, there is no problem because there are only 2 atoms. Right? So any diatomic, you take any diatomic molecules, you have only 2 atoms. So for clarity's sake, I'm just writing it as A, B. A, single bond B. Okay. And so there is only one bond. So there are no angles involved. Okay. But once the molecule becomes a little more complicated, with more than 2 atoms involved, then not only the bond length, the equilibrium bond length becomes important, but also how are they oriented? What is the angle? So I'll give you 2 examples, 2 triatomic molecules. One is carbon dioxide, other one is water. Now you guys tell me, what is the shape of carbon dioxide molecule and what is the shape of
Sir,
water?
linear,
Which is
and
linear?
water is and angular of water.
Hmm. So you say that carbon dioxide is linear. Right? And here you are saying angular. Okay, both are correct answers. Carbon dioxide is like this, and water is like this. What is the angle? So the angle is 180 degrees, and here the angle is approximately 104 degrees or something like that. Okay, but we know from sorry, we know from VSEPR theory that uh, around oxygen you have two lone pairs and two bonded pairs, right? And they are arranged in the shape of a regular tetrahedron. So if you want me to draw the regular tetrahedron, it will be more like this. Let me try to draw it for you. So one lone pair stays like that, another lone pair stays like this. Here is a hydrogen, and here is another hydrogen. Now we know that it is three-dimensional, so it's not okay. So this hydrogen is protruding out of the plane of your display, okay, your screen. So now, so this is the arrangement of the electron pairs. So two bonded pairs and two lone pairs. Now for convenience, I'm showing as if oxygen is bonded to a lone pair, but that is not an accurate picture. The more accurate picture is that one of the hybridized orbitals will be oriented. You again see, I'm already bringing in theories of hybridization into the picture. So you have the hybridized orbitals, and they are filled with the pair of electrons. This is the more accurate picture, and all of them are oriented around the oxygen along the corners of a regular tetrahedron. Okay, so the arrangement is tetrahedral, but when you want to determine the shape of the molecule, you ignore the lone pairs, right? And you have angular shape of water. Okay, so this is something we know. Now you can do the same exercise for a variety of molecules with covalent bonding, and you can predict their structure using VSEPR. Now, Avogadro is a software which can also do a uh, similar thing. Okay, so let me open up Avogadro for you. I hope all of you had installed Avogadro in your computer. So I'm going to draw simple molecules. So there is something called energy minimization that you can do. This software is a free software, so it has certain built-in algorithms, and the energy minimization is something similar to this potential energy graph. Okay, you start with the two atoms far away, and you start tracing its potential energy by changing the coordinates of these two and finding the energy of the molecule for each coordinate distance. Okay, and in this case, it's a diatomic molecule, so it's very easy because length is the only parameter that you can change. Okay, so you keep changing until you reach an energy minimum. How do you know you have reached an energy minimum? You keep changing the parameter, and after a certain point, after reaching the equilibrium distance, it will start rising again. Right? So when the energy minimum is reached and it rises, you know that you are in what is called as a potential well. Okay, you have reached a potential well. Now in the real life picture, okay, so I'll take one example which is there in the demonstration that I had shown for the other class. I'll show you now. we all know what is the most stable conformer of cyclohexane. What have you studied? Tell me. What conformer? What conformation does cyclohexane take?
The
Benzene.
chair structure,
Hmm?
chair form, sir.
Chair form, right? So let me draw the chair form. Now this is a complicated, very complicated system. So let me draw this is a chair form of cyclohexane. So I hope you understand what we are drawing here. Each corner is a carbon atom. Okay, and you have the hydrogens. Each carbon has 2 hydrogens bonded to them. And if you carefully look at each carbon, every carbon has a tetrahedral structure. Okay, so you will have C6H12. Okay, 6 carbons and 12 hydrogens. Now, how do you know that the chair conformation is the most stable conformation, which means that its potential energy is the lowest of all the conformations? What are the other conformers? There is one more conformer which is also pretty common. This is called as the boat conformation. I don't know if you guys have studied this. You have the boat conformation. I hope you understand what these are. These are the 2 hydrogens on each carbon. Okay. No, I'm just not writing hydrogen symbol. This boat conformation is also a relatively stable one, but the most stable one is this. So if you draw the, excuse me,
Sir,
yeah,
sir, like, isn't the twist boat the more stable one than the boat?
which one?
The twist boat.
Tryst boat. Okay, I'm not
Twist boat,
sure.
sir. Yes.
Okay, I'm not sure about that. So right now, just for argument's sake, let's stay with what we have. Okay, we can actually get into all sorts of details, but we will keep it a little simple right now. Okay.
Yes, sir.
Okay, even if I'm inaccurate, let's say that chair conformation is the most stable for now. Okay, because it's not exactly the point that I want to make. I'll tell you. Just 1 second. What is going on? Okay, so for now, I'm saying the chair conformer most stable. The next stable one is the boat one. Tryst boat, whatever you are telling, I'm not aware of such thing. Okay, so we'll consider that later, time permits. Okay. Okay, take a look now. See, when you draw the potential energy now with respect to the coordinate system, now in this case, you see, I am bringing in the coordinate system with x, y, z axis because it's a 3-dimensional molecule. Unlike your hydrogen molecule, which is very simple, extremely simple, here the picture is complicated. Why is it complicated? It's complicated on 2 counts. One is, look at the number of atoms. There are 18 atoms. Okay, each atom you can describe through 3 coordinate axes, and so the total number is 54 axis positions. Okay, and the other reason it's complicated is you have to bring in the electron repulsion. How many bonds can you count? I can count 12. I can count at least 18 bonds. Okay, all of them made of a pair of electrons, and not only that, there are also core electrons on the carbon. Okay, and so we have to take into consideration all these things, and you can do it only by using what is called as quantum mechanics. I hope you guys have heard about the term quantum mechanics. Have you heard this?
Yes, sir.
Yeah. So quantum mechanics is a part of physics and chemistry, where you describe each electron on an atom as a wave, and you describe it by what is called as a wave function. These are very complicated mathematical functions, very, very complicated ones. Some of them are extremely complicated and very difficult to solve. If you draw so for C6H12, how many electrons will be there? So you know that carbon has valence electrons 4 in numbers, hydrogen has 1. Okay, so 24 electrons on carbon, 12 electrons on hydrogen. So that's 36 electrons. So 36 wave functions. You have to combine them in various permutations and combinations, and you have to look at their interaction with each other as they are sharing the electrons with different bond lengths and different bond angles. So you see, on a pen and with a pen and paper, you just cannot do that. That's why you need a computer. Okay, so what the computer does is that whatever I told you, the combination of bond lengths and the bond angles, you can represent them by a combination of the coordinate system. So here I'm writing it in a very simplistic manner, just to illustrate what exactly happens in the computer software. Okay, so what happens is you change the shape of the molecule, you consider various different shapes, and for each of the shape you calculate the potential energy by, in a crude way, solving the wave function of that particular system. Okay, by writing something called as a Schrodinger equation. Very complicated. Again, I'm in no position to teach anything about this. I'm just mentioning this so that if you are interested, you can go and study these things yourself. I'm very sure at least part of it is being taught in your physics course as well. Okay, quantum physics a little bit. Do they teach that?
Sir, we learnt a bit of it in high schools.
High school in chemistry, I guess.
Sir, in chemistry and
Physics as well. Physics as well. Okay. Okay. So now I'm explaining it to you like I'm explaining things to a layman, like somebody who's not an expert. Okay. So when you trace the potential energy with this complicated coordinate system, you will have a system like this. Problem, an issue. Sorry. Uh, you will have a picture like this. Again, I'm wrong. Sorry. Something like that. So this is for the molecule, the complicated molecule. So let's say that you start with a structure, a random structure where the potential energy is high, and you start doing what is called as energy optimization. So what the computer does is it will start twisting the molecule by randomly changing some of the coordinates of the atoms. Okay, how does it do? I don't know, and it's built in. So we know we can do it only by click of a button. Okay, so let's say that it starts at a high potential energy value. So it starts twisting and starts seeing that as the coordinate system is changing, the potential energy drops, and it drops to a lower level. How do you know it has dropped to a lower level? As I told you, once you drop to the lowest level, any more twisting will result in an increase. So that way you know you reached what is called as a minimum, potential energy minimum. But there are two types of minima that are available. There are something called as a local minima and something called as a global minimum. Okay, so you like it's like this. See, Chennai city is on, the coastal area is on mean sea level 0 meters from the mean sea level. So I can say that Chennai city is at the mean sea level and it is very low, but it is not the lowest point on earth. Where is the lowest point on earth? Anybody knows? The
Mariana Trench.
Mariana Trench.
No, 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 no. When I say the lowest point on earth, I'm talking about exposed land area with respect to the mean sea level. Mariana Trench is the deepest point on Earth's surface, but it is under the ocean. I am talking with respect to the mean sea level. And now, can anybody answer me? Nobody knows? Which is the lowest
is it the
exposed? Huh?
Sir, is it the Dead Sea Depression or something?
Yes, it's the Dead Sea Depression. It's around 400 meters below sea level in Israel. The place is in Israel and Jordan. The sea is shared between these two countries. I've been to this place many times. So if you type Dead Sea on YouTube, you'll find people floating on the water, and that's the most popular video that you'll ever see. Okay, so even though I say that Chennai's level is 0 and it is very low, it is not the lowest ever, right? So the lowest exposed land area with respect to the sea level is in Dead Sea, minus 400 meters below sea level. The next exposed level is also in Israel in a different place, okay, called the Sea of Galilee. So if you know a little bit of history of Christianity and Judaism, you'll get to read about these things. I don't know how many of you will be interested. That's not my point, but these are popular places. That's why that's what I'm trying to tell you. So getting to a minimum like this is like saying Chennai is the lowest. Chennai coast is the lowest point, but there exists another minimum. So let me redraw this minimum properly so that it looks clear. Let's say that you have another minimum like this, below which there is no other part of the potential energy graph with such low potential energy. So this is a global minimum, okay, and this is a local minimum. So when the computation happens, sometimes you reach a local minimum and you think you have arrived at the most stable structure, but there exists another structure which has even lower potential energy, but there is no way you can reach that because you don't know, because it's all like groping in the dark. So computational chemists, they're such experts that they can actually find, there are methods to find global minima, but they are complicated and it requires experience. Okay, now there are many softwares, very expensive, very expensive softwares. They're not free softwares, very expensive ones, where the entire Schrodinger equation for a molecule is considered, of course with several approximations, because you cannot actually solve the exact Schrodinger equation. Approximations, and then you solve and you find the energy minimum considering all the electron wave functions. In Avogadro, you don't do electron wave functions, but they have a slightly different method called as force fields. Please don't ask me what a force field is. I'm not an expert. I don't know how to explain that. But they don't consider the wave functions. Wave functions are very accurate descriptions. Force fields are slightly approximated, inaccurate pictures. But still, they can be very helpful in getting you an approximate idea of how the molecule is oriented, particularly for large systems. And computationally, it takes lesser amount of time to achieve this. Okay, so there are softwares. There are several softwares. Like one of the most common, very popular one is called Gaussian. It's a proprietary software. It's very expensive. If you want to have a license, it costs around approximately 3 to 4 lakhs for this software. There's one more which is called a Spartan, and there are many others. These two are pretty popular, and there are many others which will do the wave function method of minimizing the energy. And Avogadro use what is called as a force field. Okay, so you can do energy minimization. It is not 100% accurate, but for small molecules, it's more or less accurate. Okay, so I'm going to demonstrate how you can find the conformers and also predict the VS-EPR predicted structures. You can verify using Avogadro. So that's what I'm going to demonstrate now. So now I have spoken for around 10 minutes already. Sorry, 30 minutes. So let me go there. Okay. So here is your Avogadro software. Okay. So there are several menus available. So usually you will be interested in the drawing tools. So in your software, go to the toolbars and select the draw settings so that you have them here. Okay, so here are the draw settings. So the most important part of this is the set of tools which are here. Okay, so I have isolated them. I can put them back here like this. Okay, so let's take a look. First one is draw tool. Second one is navigation tool. Third one is bond centric manipulation tool. Fourth one is manipulation tool. Selection tool, then auto rotation tool, auto optimization tool, measurement tool, and align molecules tool. So this align molecules, I don't even know how to use this, not very useful. You guys can explore it later when you have leisure time. The most important ones are the draw tool, the manipulation tool, the selection tool, and the auto optimization tool. These are the most important ones. So let's start with carbon dioxide. So how do you draw? So here are the most common elements that you can select. Okay, so carbon, I'm going to select carbon, and I'm going to select double bond because I know that carbon oxygen has a double bond. So let's draw that. So first I draw carbon, then I select oxygen, and on one, so okay, by default when I draw carbon, automatically it fills the valency, normal valency of carbon with hydrogens. Okay, so that's because we have enabled add hydrogens, so you can remove the hydrogens. So you see it's removed now. Okay, so by the scrolling the wheel on my mouse, I can make it bigger or smaller. Now I'm going to draw oxygen. How do I do that? What I'm going to do is, I have already selected oxygen and a double bond. I'm going to left click on carbon, hold, and then drag. So you see, I'm clicking, I'm dragging, and I'm leaving. So you see, automatically it draws a carbon oxygen double bond. Now two hydrogens are automatically added. Okay, now so this molecule right now is formaldehyde. Okay, now I have to draw another carbon oxygen double bond. So I click on carbon, I drag, and I'm drawing another oxygen, and the moment this is drawn, the two hydrogens are vanishing. Okay, so I deliberately have drawn it with wrong shape. We know that carbon dioxide is not angular shaped. Okay, so now I'm going to minimize the structure. Okay, so what I'm going to do, I'm going to click on auto optimization tool. Okay, the moment you do that, there are few options coming here. So there are force fields, several force fields available. UFF, Chemical, MMFF94, MMFF94S, UFF. So many are there. You can actually select any of them. Okay. So, and then there are two algorithms, steepest descent and conjugate gradients, and there are a few more also, but we can use the steepest descent one. Okay, I don't really exactly know statistically what these mean, but if you guys are interested, just type on Wikipedia steepest descent method or the conjugate gradients, you will get the mathematics of this. Probably you already know this, I don't know. Okay, these are some statistical methods of algorithms to reach the minimum, the energy minimum in the potential energy plot. Okay, so I'm going to start. So please remember that this molecule is so small, the computation time will be very small. Okay, it'll be done in just a couple of seconds, and you will see here once I click start. Here there will be a few numbers which will be displayed, and one of them will be dE, that is the difference in energy. Okay, so the coordinates will be changed until dE becomes 0. So what does it mean? It means if you draw the tangent at the minima, okay, the slope will be 0 because it will be parallel to the x-axis. That's basic mathematics. So that's what it means. Okay, so it has reached a minimum. Whether it's a global minimum or a local minimum, that's where the big challenge is. And with the carbon dioxide, you will not face the challenge. I will explain it with uh, what is that? What's the other molecule? Uh, Cyclohexane. So let's start now. Okay, I'm selecting UFF. I'm going to start. You see, it's done. Just in 1 second, it's done. Excuse me, guys. Okay, so you see, within a second, the calculation is done. D becomes 0. Of course, it doesn't stop. So now I can stop. Now uh, you can simply click outside the molecule and you can start rotating it in 3 dimensions. You can check. You can inspect the molecule. You can see that it is linear. Okay, and so it works well. Now you can use measurement tool. Oh, it's obvious that the angle oxygen carbon oxygen will be what? It will be 180 degrees. So there's no point in measuring that, but you can measure the distance, the bond distance. It says 1.196 angstrom between carbon and oxygen. Okay, as I told you, please don't ask me what a force field is. I'm not an expert in computational chemistry. I hope I am, but I'm not. Okay, so uh, it is one of the methods to optimize different structures, but much larger ones like DNAs and proteins and stuff like that. Now you can change the view. Like here right now it is a ball and stick method, so you can I have removed that. I can usually you can go by looking at stick models like this or wireframe like this. You see, this is the wireframe model of carbon dioxide. Doesn't make much sense. So we'll go to the ball and stick. Now for some other molecules, wireframe will be very helpful and I'll explain to you soon. Okay, so carbon dioxide. So this is carbon dioxide. Now I'm going to click on the select, control all, delete. So it's gone. Okay. Now let's try one more molecule. So I click on draw. I select oxygen, but this time I'm going to select single. Okay, why? I'm going to draw water molecule. So here is water. I'm going to remove the hydrogens. Now I'm going to draw the hydrogens manually. Okay, so I click on it, drag. So I introduce a hydrogen. Okay, I'm introducing a very large, very large bond length. So let's measure it. Click on this one and click on. Okay, where is that? Yeah, so I clicked on these two. And it's coming to 3.5 angstroms, which I know is not the bond length of oxygen and hydrogen. Okay, so deliberately I've done like that. Now I have to draw the other hydrogen. So let me do that. So I click on oxygen, I drag. This time I'm deliberately drawing a linear one. Okay, so I'm doing all this to know sorry. Yeah, see, it's linear. You know that water molecule is not linear. So let's see what energy optimization does. So I click on this UFF method. I'm going to start. That's it. See, within 2 seconds, the program has minimized the structure, and you can beautifully see, you know, water molecule. Okay. Now, in some case, so okay, let's measure the bond lengths, bond angles particularly. So yeah, so I'm selecting 1, 2, 3. The bond angle is 104.5 degrees, which I think is the angle between oxygen, oxygen, and hydrogen. Okay, great. So wonderful. Now I'm going to give you as a homework at least 10 to 12 molecules which you are going to work and produce a report which I will tell you how to write. Okay, so I will come to that a little later. Now I'm going to click on select. It's already clicked. Okay, now I'm going to click Control A, select all, and I'm deleting. Okay, so I demonstrated with carbon dioxide and water. Now let's go and do some complicated stuff. Okay, click on Draw tool. I'm going to draw cyclohexane. Okay, so here in build, I'm going to remove hydrogens. I click on that. So first carbon. Okay, so let's remove the hydrogens. One carbon. So I'm going to draw another carbon. So how do you do that? Click on carbon, drag until you get the other carbon. Click and drag. Now see, the moment I do this, hydrogens are added automatically. Don't bother about it. Click on carbon, drag. Click, drag. Click, drag. Now go to build, remove hydrogens. See, I've drawn a picture. Which is completely planar, nothing to do with, not even a resemblance with the boat or the chair form conformer that we know, correct? So this is your cyclohexane without the hydrogens. I'm going to build the hydrogens now. So add hydrogens, the hydrogens are added. Okay. Now I'm going to I'm going to do the energy minimization. Now I'm going to tell you, before even doing it, by doing the energy minimization, we may reach the global minimum, in which case it should result in a chair conformer, or we may reach a local minimum, and we do not know what that conformer may be. So let's see how it works. Okay, so let's click on E. I go with the same method. I simply start. Okay, see. Do you see the energy minimization? You can see, take a look at this. Energy is getting minimized. It's coming closer to 0. Now it is minimized. It is 0. Okay, so let me stop it. Now let me analyze. So click outside the molecule and see. Okay, it looks very complicated. So let me go to build, remove the hydrogens. Does it look like it has reached the chair conformation? You cannot say very clearly with ball and stick model, but it does look like that. So let me go to the display menus, uncheck ball and stick, and go for wireframe. Now what do you see? What do you guys see? What shape is this? Guys, do you hear me?
Yes, sir.
It is the
Yes, sir.
chair conformation. Chair conformation. Looks beautiful, right?
Chair, sir. Yes, sir.
Look at this. If I orient it this way, it looks like planar. But if you move it, you know that it is a chair conformation. Okay, so let me build the hydrogens. Now you can see the hydrogens. Looks beautiful. Now in the previous class that I taught, for which the video is available, when I was trying to do the minimization, it did not end in a chair conformation, but it went to some other conformation. So it took us a little bit of time to achieve this by doing some random distortion to the molecule. Okay? Does it sound interesting, guys?
Yes, sir.
Yes.
Yeah.
Yes,
So
sir.
you got your chair conformation. Okay? Now, like this, you can verify the shape and structures of simple molecules and some complicated ones as well. So let's try one more thing. Okay, what other molecule do you guys want to try? Can you guys tell me? Let's do one more, and then I will give you a little exercise to do in the class itself.
The benzene.
Benzene. Okay, let's do benzene. Now, in the case of benzene, you have to select double bond. Okay, so let's click and get the. Sorry. Okay, in this case, you can go for ball and stick. It will be easier. Okay, so remove hydrogens. Click and drag. So you'll have carbon-carbon double bond. Click and drag. Click and drag. Click and drag. Click and drag. Okay, now this molecule is completely wrong, right? Why? Because you know that alternatively I have,
Everywhere,
yeah, everywhere it is
everywhere is a double bond.
double bond, which is not correct. So let's try to, I don't know. Yeah.
So one carbon is more also.
Oh, is it so? So let's remove this. So select this and I'll delete it. So one double bond, another double bond, and you don't have another double bond. So click on double, click on this. Okay. Now is this molecular structure accurate? We don't know. So let's see. So click on navigation tool, click outside the molecule, and you just randomly check. Okay. It looks flat. We know that benzene is flat. So let's distort it. Okay, so go to the manipulation tool, the hand tool, click on the atom and distort it. See, I'm totally disfiguring the molecule, right? So you can do this as many times, as many random combinations that you want. It's up to you. Okay, now let's see what we have done. Is this benzene? Does it resemble anything close to benzene that we have studied? No, right? We know that benzene should be flat. So now let's do the energy minimization. So I'm clicking on E, not changing anything, just start. That's it, done. See, it's minimized. I'll click stop. Now, do we know the structure? Yes or no?
Yes, sir.
Yes, sir.
Yes, we know, right? And let's measure. Okay, before measuring, so let's undo this. You see, beautiful, beautiful benzene molecule. See, it's totally planar. Right. So you guys can play around this way. Okay. So we can do one more round of playing around. So let's see. Let's see. So I'm going to make another molecule from here. Okay, let's select ball and stick. This time I'm going to do what is called as a biphenyl. I don't know if you guys know what a biphenyl molecule is. Have you heard about biphenyl? I'll draw the structure. You see, this is benzene.
Sir, two benzene rings fused together.
Yes. Yes, not fused. They are like this. Okay, two
Yes,
benzenes,
sir.
two carbons are joined together by a single bond. Okay. Now these two benzenes, they may be planar, they may not be planar. So sometimes one molecule will be like this, and the other molecule okay. So this is planar. Like sorry, this one is in the plane of the this display, and this one is perpendicular. So this part is protruding out. Okay, and this part is on the other side. So they are at right angles. The plane of this molecule and this plane of this molecule are at right angles. So these are some confirmation. So we can verify whether such a thing can happen here. So let me draw. Okay, 5, 6, 7. Okay, now let's make some of them double bonds. 1, 2, and 3. Okay, let's remove the hydrogens. Now let's take a look at this molecule. What is the shape? Now they are looking planar. So let's distort them as usual. So we love to do that, right? At least I love to do that. Now it's distorted. Let's distort all. Why distort it only one way? So now you see these molecules are completely distorted. Now let's do the energy minimization. I go here, simply click start. Now you see beautifully it is getting optimized. Energy is slowly becoming closer to zero. Will be optimized pretty soon. You see it's optimized now. Now let's explore. Are they looking planar? Yes, they are looking planar. Very good. Excellent. Okay. Now this is a minimized structure. Now I'm not sure if this structure belongs to a local minimum in the potential energy graph or the global minimum. Okay. So one way to do that is what you do is you start your energy minimization. So you know that it is running. See, even though it has reached the minimum, it's still running because it says stop here. Okay, now while it is running, I can actually distort. I can introduce a distortion like this. You see, I can introduce a distortion, and every time you introduce a distortion, you will notice that the dE value will increase. So that way, some random distortion you are introducing, you see, very beautiful, right? It's amazing how this algorithm works.
Yes, sir.
Yeah. So you can do this and then verify whether we are reaching the same confirmation again and again. So now I'm stopping. Let's see. You see, more or less the same, right? Okay. Now let me do one more little trick. Okay. So in organic chemistry, have you guys heard of something called atropisomers? Anybody? Okay, you guys have not heard.
So can you
It's a little
repeat the word, sir?
atropisomers. I'll write it here. Atropisomers. Okay, I'll tell you what they are. Okay, see, for a simple biphenyl, this molecule is called as a biphenyl. Okay, for a simple biphenyl, there is free rotation of this benzene ring with respect to the other benzene ring. They can freely rotate, but the most stable, one of the most stable structure is the one where the two rings are planar. Okay. But when you introduce certain bulky groups, like for example, you introduce a methyl group here, and you introduce a tertiary butyl group here, or two tertiary butyls also you can introduce. When you introduce these bulky groups, the two rings cannot rotate freely. So they will be frozen in such a conformation that there is maximum distance between this group and this group. Okay, so what will happen? There will be a permanently twisted form. So they both will not be planar, but they will be twisted with respect to each other. It's called as a dihedral angle. So let's try to do that now. Okay, I'm going to introduce a methyl group here, and I'm going to introduce a tertiary butyl group here. So let's see how it works. So carbon single bond, I'm going to introduce a methyl group. Okay, now I'm going to introduce a tertiary butyl group where there's three hydrogens should be replaced with a methyl group. So I'm click on this, automatically becomes a methyl group, another methyl group. Now I'll rotate it a little bit so that the other side is exposed, and this hydrogen also should be replaced. So all I do is just click. So now what I'll do, go to build, remove hydrogens, and control Z, and I'll just verify if my structure is correct. You see, what you see here is carbon, 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 carbon. So this is tertiary butyl group, and the other side you have a methyl group. Okay, you know what? Well, let's do this. Select it, put it here, delete this. Let me introduce the methyl group on this side itself. Okay, so now go to build, add hydrogens. Okay, so what I'm telling you right now is that you see the tertiary. Okay, let's remove the hydrogens for clarity. See, this is a bulky group, the tertiary butyl group, and there is a methyl group. So there will be repulsion between these two groups. As a result, this most probably this methyl group, this benzene will twist and turn almost 180 degrees, so that this methyl group will come this side, so that it stays far away from the tertiary butyl group as possible. Okay, now we don't know what exact conformer it may take, so let's try. Okay, so go to energy optimization, just start. Okay, so it has stopped in this position. Okay, and let's analyze. Because of a little bit of experience, I am expecting that this is a local minimum structure. So let's see. Now when I rotate it, do you see that? Do you see what I'm saying?
Yes, sir.
Yeah, take a look. This is one of the benzenes. Look at its plane and look at the plane of the other benzene molecule. How do you move it? There's one way to move it. Do you see that, guys?
Yes, sir.
The benzene planes are now different. They are not coplanar. Do you see that? This is happening so that
Yes, sir.
this methyl group stays far away from the tertiary butyl group. Okay, but still I think that this is not the ideal shape. The best shape will be when the metal, this whole thing twists and turns so that it comes here. So let's see if we can reach that by a different method. So let's go to chemical and start it. No, it's not really doing that. So let's try another one. So let's try this. So these are some of the fun things that you can do with the molecules. See, now they are twisting, turning. I hope. Okay, so this one has reached something like this, right? So let's try one more. So that is also not working. So this one is taking longer time, but not much of a difference. So let me distort it as the program is going on. So I'm distorting it. So it's taking longer time. So I'm going to stop this. Let me go to the original one, UFF, and I'll restart it again. So let's see what happens. Okay. So now it has reached a confirmation where what I believed kind of has happened. But still, I'm not 100% sure if this is a true picture. Okay. But this is one of the confirmers which probably is very helpful in understanding the energetics. But here in this confirmation, take a look. These two groups are far away from each other, but the two benzenes are planar. So, which one could be the real picture? So, these are the questions that computational chemists deal with on a daily basis. Okay. Now, so this is where computer modeling softwares like this can really be very helpful. Now, a molecule like this, it doesn't matter. It doesn't matter whether it's taking this shape or that shape. As far as the science is concerned, it's important. But when it comes to the applications of these kind of models or this molecule, may not be great applications here. Okay, but where it becomes very helpful is, uh, for example, you want to develop a coronavirus anti-coronavirus drug. Okay, so you have several targets on your coronavirus uh, the surface, because the shape of the virus is known. The entire The RNA code is known, the genetic code is known, and the type of proteins that are there on the outer surface, they are known. But what is not known is what molecule can you synthesize in your laboratory that can go and bind to these proteins and deactivate it. That's something that is not known. That's one reason why a drug that will treat you with the corona disease has not been discovered yet. I think they are coming to a breakthrough. Soon it will be out, but not there out yet.
Sir?
Yeah.
Sir, like, isn't remdesivir like doing the same thing as you told? Like, it's a protein which bonds to the its RNA, and it doesn't allow the chain to continue further.
You know what, remdesivir, and there were a few other drugs. These are drugs which were actually designed for some other they were antiviral drugs targeted at something else. I think remdesivir uh, was designed as an anti-HIV drug, I think. Am I right? I'm not sure.
Sir, I don't remember that much.
Yeah. Yeah, I can check it for you. So let's try it. It's a broad spectrum antiviral medication developed by Gilead. Okay, was originally developed to treat hepatitis C. Okay, do you see that? So you have a molecule like this. This is remdesivir. Few things you can notice. This is actually a sugar molecule, a modified sugar molecule, from which to which another part is attached. A phosphate molecule is here, and there are different substituents. And so when you do energy minimization and consider different conformers, there will be millions and millions of conformers for this molecule, millions of them. Which conformer will fit well so that it interacts with a certain part of the virus to deactivate the virus? That is a trillion-dollar question actually. That's where computational chemists really play a vital role. They can play a vital role. Okay. So drug action, usually you talk about activation. So you see, we may not understand much, but let's see. Mechanism of action. Look at this. As an adenosine nucleoside triphosphate analog, the active metabolite of remdesivir interferes with the action of viral RNA-dependent RNA polymerase and evades proofreading by viral exoribonuclease, causing a decrease in viral RNA production. Okay, now most of it we don't understand what the hell they're talking about, but one thing is important. It says interferes. Do you see that? So what it means is there is a certain action that is taking place in the normal biochemical pathway, and this remdesivir goes and blocks that action. Right? So this is how drug molecules work. So let's take a look at paracetamol. This is one of the easiest one we can all understand. Paracetamol, which is something I think you studied a little earlier also in your course. Okay, so let's see interactions. Before that, overdose, use in pregnancy, adverse effects. How does it work? Okay, here prokinetic agents such as accelerate gastric emptying. So some nonsense is given here. So let's see. Look at this. Paracetamol appears to exerts its effect through two mechanisms: the inhibition of cyclooxygenase and actions of its metabolite AM404. We'll forget it, this one, but there is an enzyme called cyclooxygenase, and it inhibits its action. Right? So You know, it's like I don't know how many of you have seen this when you watch cricket, you see the batsmen wearing gloves. Okay, so they have 5 fingers, so they should have a cricket gloves having 5 fingers. But I don't know how many of you have noticed. Many times the gloves have only 4 fingers, in which one particular pocket for the fingers, two of the fingers should be inserted, not one one finger for each of those pockets. Have you noticed that? Anybody? Cricketing gloves?
Yes, sir.
Yes, sir.
Yeah, it's very common actually. If you take a look at them, you see this. Why am I telling all these stories? See, five of them here. Look at this. 4 of them are there. No, I think the other one is not seen. But some of them will have only 4. One for the thumb and 3 for the other fingers. So 2 of them will be together. Okay, I don't see them here, but if you really search for them, you'll get them. You know, these pictures. I really thought that I could get. I don't see them. So let's go to images. Why am I giving this example? The example I'm giving this because 2 of those fingers, for some reason, you know, people who study biomechanics and this product development, they have decided that those 2 fingers should be kept together and they should not be moving independent of each other. So they both go into one single pocket. Okay, you guys can try to find out why. Okay, similarly, cyclooxygenase, a particular enzyme, it will it will fold and unfold in a certain fashion to do its function as an enzyme, as a protein. Okay, but see, look at this picture. See, 1, 2, 3, 4. So these the index finger and the middle finger go together into this. This is what I'm telling. Okay, for some reason they should be together. That's what some company has decided. There should be some reason, some science behind it. Maybe, I don't know. Similarly, any enzyme action has to go through a series of change in the molecular structure so that it does its function. And drug molecules, what they do is they will go and bind with the protein or the RNA or DNA, whatever it is, and inhibit that function. It will stop that function from happening. And that's how you have drug action. Now, how is it related to computational chemistry? Because what shape of the molecule should be considered for an optimal fit into the biomolecule. That's where it becomes important. Okay, so there are many sophisticated software which can do those things. But what I demonstrated to you is the importance of finding conformers and understanding how they can play a role in finding the right shape of the molecules. Okay, now I'll stop here from lecturing. I'll give you some homework. Okay. And what you guys have to do is you guys have to draw the molecules, simple molecules. I'm going to give you very simple molecules. You have to draw the molecules. You have to do the energy minimization, optimization that I demonstrated. And once you reach the optimized structure, I want you to take a picture. Okay, so let me explain with one example. What example can I take? I'll take ammonia as an example. Okay, so this is how I want you to do. So let's take ammonia. So again, so click on select, control. Now I'm going to draw ammonia. So nitrogen. I select ball and stick, and I select. I go to build and remove hydrogens. So there's only nitrogen here. So I'm going to 1, 2, 3. Okay, we know that this is not the ammonia structure, so I'm going to minimize it. Okay, so I go here, I start it, and it's minimized. Done. Okay, so it's pretty fast. Okay, we know that. Okay, so see, it is showing the wrong structure. This is not the structure of ammonia. We know that it is not trigonal plane. It's not a planar molecule. It's a pyramidal molecule. So let's select some other method and start it. Again, it is showing.
Ah,
Yeah, now you see it is pyramidal shape, right? So this is the right structure of ammonia. So I'm stopping it. Now I'm going to generate a report. I'm going to make a report. How do I do that? So you open your Word file. A blank document. Okay. So use your snipping tool. Okay. Then you take a picture of this. So you take a picture of this. And I copy and I paste it here. So I will write ammonia. Okay. So who is that man? Your mic is on. Okay. So here is the molecule. Then I will write bond length. How many bond lengths? How many bond lengths will be there? There will be 3 bond lengths, right? So give the bond lengths. So what you can do is you go to Avogadro. Here in the display, you give label. Click on label. So you have nitrogen 1, hydrogen 1, hydrogen 2, hydrogen 3. Okay, now you go to measure tool. Click on hydrogen 1. Is it? Did I click it? Am I measuring? I have selected hydrogen. Now I selected nitrogen. So hydrogen 1, nitrogen distance is given here. So you write that distance in angstroms and write also the angle. Okay, so H1 and H2 angle. What is the angle? You write it, and like that you give the other angles also. Okay, so like that I want you guys to make a report, and I'm going to give you some structures which can also be analyzed using VSCPR. Want to the final structure that you arrive at should be correlated with the VSCPR structure that you will arrive at as well. So I want you to do this little exercise. Okay, so I'm going to give you a series of compounds. So yeah, thanks Ishwar. Neeraj Kumar Yadav, he has kept his computer and gone somewhere, and we all could hear what's happening on the other side. Okay, so let me give you the molecules. Uh, just 1 second. Where are these? Here. So I want all of you to note these things down. I'm also noting down. I will show you in a minute what these molecules are. So the molecules are SO2, then BF3, ClO2, PF3, XEF2,
sir.
N. Oh, yeah, I'll show you. Don't worry. I'll display them. Right now, I'm writing it on my sheet. I will display. Don't worry. N2O, BrF3, SCl2, HCl, SF4, SF2, CH2. Okay, so let me display them for you. Uh, I know that you guys we are running out of time, so just last little bit, and I will leave you guys. Okay, so these are the molecules. Try as much as possible. Don't simply say I tried one and I'm submitting it. I want you to try at least 10 of these. So let me number them. This 1, 2, 3, 4, 5, 7. Quite a few are there. 8, 9, 10, 11, 12. Okay, 12 molecules I have given. Try at least 8 to 10 of them. Okay, so draw the structures. Of course, for example, a molecule like HCN, you should know whether it is H single bond C single bond N, or H single bond C double bond N, or H single bond C triple bond N. You should know that. So that's something you can arrive at when you consider Lewis dot structures. I didn't explain how to do the Lewis dot structure. If you don't understand, if you don't remember, go ahead and textbook. Okay. So from Lewis dot structure, you can arrive at. So for example, in HCN, it is H single single bond C triple bond N. Okay. In CH2O, so let me also underline the central atom in all this. Here it is sulfur, here it is boron, here it is chlorine. I think it is N2O is this one. I'm not 100% sure. No, I think it's one of the nitrogens. Is the central. Okay. Okay. So these are the molecules that I'm giving you. You draw them on your Avogadro, do the energy optimization, compare the shape with VS, what you may get from VS EPR. See if you can actually verify them. If you are getting a wrong shape, it means that you have reached a local minimum. Point இருக்கு. Ah. So you have reached a local minimum, which means that you need to do the optimization a little bit more with some distortion introduced into the molecule. Okay, so you guys do this, and you will be able to
Sir,
appreciate. Yeah,
and we
tell
have
me.
to find the angles also, no?
Yeah, try to find the report the bond angles and the bond angles and the bond lengths. And if
Yes,
you are in a position to find out the structure, like you can put a name for the shape, you put the shape also.
yes.
That will make a very nice report.
Okay, sir.
Right, guys?
Yes, sir.
Yeah. I will share this document in the in our teams as well. Okay. Wonderful. I think I'll stop here. A lot of things we discussed, and so today is the